Welcome everybody. So today we are going to try to talk about collisions by unifying what we already know about two conservation laws, conservation of momentum or the impulse momentum theorem, and conservation of energy or the work energy theorem. And in particular, we're thinking about collisions, right? So things that are crashing into each other. Whenever you're going to think about a collision, the number one thing to do is make sure you define your system really carefully so you know when you can apply these conservation laws. When you're approaching a physics problem from the perspective of a collision, you almost always want momentum to be conserved, which means you want to choose a system. You want to choose a system where J is equal to 0. Now that's not always possible, but usually it is. If it's not, then you can go figure out what J net is by calculating the net force acting on your system. But one way or the other, if you know what's going on with your change in momentum, you can then talk about some different kinds of collisions that depend on what we're going to do with this other conservation law. Now, we know from working with energy a couple of weeks ago that there's lots of different kinds of energy that might be involved in the changes in the internal energy of a system. And when you talk about changes in potential energy, collisions can get complicated really fast, especially because there are even some other forms of internal energy that are not well represented by potential energy. Things like reconfiguring of an object that happens if it crashes and crumples, or thermal energy or sound energy. Those are all things that are hard to capture here. So often, rather than use the full version of the work energy theorem, what we care about in a collision perspective is, does the kinetic energy of the system change or not? So that's the thing that you're going to look at to figure out what kind of collision you are dealing with. The options are that the kinetic energy might not change, in which case you're dealing with an elastic collision. This is sort of the most straightforward, easiest to solve collisions. But you might be dealing with the situation where the change in kinetic energy is less than 0, is negative. Your system is losing kinetic energy to one of those other things that I mentioned. And then you're dealing with an inelastic collision. And the classical example of an inelastic collision is if you have two cars, for example, that collide, get stuck together after the collision. That's a really strong cue that you're dealing with an inelastic collision. And in particular, if they do stick together truly, what you really have is a perfectly inelastic collision. So they're called perfectly inelastic collisions. And they usually are when the final velocity of each object in the collision is the same. And then you can also have collisions where stored energy of some form is released. This is something like an explosion or an eruption. And that will mean that you get an increase in the kinetic energy of your system, and you call that a superelastic collision. Now, the reason that it's important to keep track of what kind of collision you're dealing with is because it tells you what you're allowed to do with the kinetic energy of your system. Whether you're allowed to think of it as not changing, which might give you an extra equation, as going down, where this is the condition that you might be using, or where the kinetic energy might actually be going up, and then you would need to know something more about how you got that energy.